Okay, so today we are going to go over neutralization reactions, and this is the chemical reaction with an acid and a base. So let's do this. Like always, we're going to start with a definition. So a neutralization reaction is when a hydronium ion reacts with a hydroxide ion. To form water. Water and salt. And it doesn't have to be like table salt. Salts are just like a metal compound that reacts with something else. So I'm going to give you an example real quick. So the way you write this, you have H3O plus OH negative. This is like the shorthand way of writing it, leaving out the salt part, which would be the metal. So you have H2O. So this translates to this. We have hydrochloric acid plus sodium hydroxide is equal to NaCl, which is your salt, plus water. And if you look at the actual reaction and balance it, you can kind of see that's going there, that's going there. So it's kind of like a double replacement, but not really. It's just this happens due to the ionization. So like, let's draw one of my famous beakers. Okay, so like, say you had HCl, and then you had NaOH. And they're both getting dumped in here. So, anyways, what's going to happen is you have Na plus, OH negative, you have some water in there already because that's what the solution is. And then we have some H plus and Cl negative. So what's going to happen is that's going to go to there. That's going to form more water. This is also going to pick this up, but really not. I mean, not really in this instance because the hydroxide and the hydronium are going to join together to make more water. But if you had just reacted it with water, then yeah, it would pick it up and make it more acidic. This is actually going to neutralize it and make the pH close to 7. I still wouldn't drink this, but I mean, you know, it does make water. Anyways, so, and this is totally not how you usually mix this. Most of the time when you're mixing an acid and a base, it's to determine the concentration of an unknown. And what you would do is you would have an instrument called a burette. And let's, it's got like a little tip there on a ring stand. And then you'd have like a little flask here. Let's fix this. And then you'd have like some unknown acid or base. Like you might know what it is, but you won't know what concentration. And then up here, you're going to have either known concentration. Sorry, I'm getting off topic, but I felt this would be kind of a cool real-world example of explaining it. And then this would be acid or base. Just depends on what you're titrating with. And then what happens is, you know, your liquid would mix with this, and then you add in It's a horrible dropper, but you get the point. You add in a small amount of indicator, which is this. It's clear, but it's called either, depending on what you're mixing it with, it's usually phenolphthalein, and I don't even know how to spell that. I think it's something like this. I don't remember. It's phenolphthalein or like, I think it's bromo blue for the acid, but I don't remember off the top of my head because I don't like memorizing experiments. But what happens is when the solution gets slightly more basic or acidic, it has a color change. I know for sure, because usually you're going to titrate the base into the acid in most experiments I've seen. So they use phenolphthalein for that. And what happens is, as soon as it gets just a tiny bit more, like there's just a little bit of hydroxide in there, the solution will turn pink. And that's when you're able to be like, oh, I used like, I don't know, this much of this. And that's where your molarity comes in, because you know how many moles of it you used. And the moles of the acid equal the moles of the base. In determining, using like the amount of liquid that you usually, it's something small like 10 or 20 milliliters, you're able to calculate the molarity and figure out the concentration. It's pretty cool. I was actually planning on doing this with you guys in class, but that obviously didn't work out, so we're going to be doing a virtual lab. I'm going to try and find a titration one for you guys, but that's going to be like a project in the future. Right now, you're going to be doing a pH one and comparing like solutions and stuff like that. Anyway, sorry I got off topic. I figured, this is something kind of cool for you guys to see why this is important and why you would use it. Anyways, so before I got off on that, you don't have to draw any of that. It was just for you guys to see. So when a solution of strong acid and strong base react, or not react, I'm going to just put mixed. I need to have like a script when I'm talking, so I always say things out loud, and I should just have a script. Anyways, the H3O plus and OH ions combine to form water. Maybe I already wrote that down, I don't remember. So there's a demonstration that I was going to do. Obviously I can't do that, but that's why I drew this stuff. I was going to mix lime water with phenolphthalein, and then pretty much you blow air into it using a straw, forming carbon dioxide, and then the solution will turn clear because lime water is calcium hydroxide. So there is a way to do this. I'm going to explain it when I go over the pH scale, where you guys can actually try this at home with some, I think it's cabbage leaves. I have it written down so you guys can try it. It's super, super interesting, but it's just in case any of you are interested. All right. So that would be for that. And this was all for strong acids. Now, we're going to go on. That was for strong Arrhenius acids. Sorry, I misspoke. So say we had HF plus H2O. And then we have a strong Bronsted-Lowry. Wow. So a strong Bronsted-Lowry acid will produce a weak conjugate base because a strong acid dissociates easily. So, therefore, the conjugate base would only need a little attraction for protons since they are, given up so easily. So let me write that down. Therefore, the conjugate base would need little attraction for protons because they are given up so easily. Note, the same thing works for a Bronsted-Lowry base. And then one more thing, I probably should have gone over this before, but we have amphoteric. So we have amphoteric molecules. Substances that can act as both an acid and base by being a proton acceptor or donor. So this would be substances that can act as both proton acceptor and proton donor. So a strong example of this is water. Water is amphoteric. So reason being, if you write out its equation, you have OH negative plus H3O plus. So that would be an example of that. I'm going to give you a second to copy that down while I go to the pH scale. I'm going to turn my lights on because I can't see. Alright, so we're going to continue on to the pH scale. And I'm only going to touch on a little bit of this right now because, no, actually I got time. So, pH, because I kind of had a short video, so let's make up for it. So, pH is the power of hydrogen. So, it expresses how acidic or basic a solution is. So, remember I wrote this down before, but we're going to do it again. Preferably with straight lines, because and then let's do that is not what I want to do at all. Alright, you're just going to have to deal with this because I'm not going to finish. And put some orange in there. Alright, so if you ever look at those litmus papers, you know how they have like red, orange, maybe some yellow on there. There we go. And then probably a little more orange than that. So on the other side, you have your bases, which you're going to start off with like some light pink. And then it's going to go to like some light blue color. It's really just going to be almost blue and pink all the way through, but it's fine. Obviously, what I can do with mixing paint colors is limited on this, but anyways. If you want to do it with colors, feel free. So basic, acidic. Alright, so that's kind of like the pH scale. I just kind of drew the colors in there because it mimics the litmus paper a little bit. I mean, it's not perfect, but you get the idea. So the more basic it gets, the more blue the paper is going to be. The more acidic something is, the more red it's going to be. So, interestingly, and I was right, it's red cabbage. So red cabbage is a natural pH indicator. So if you want to try this at home, you can. It's perfectly safe. So what you need to do is chop it up and boil it to separate its flavin. So chop it / boil it. Although don't really like waste food now because, you know, all the stuff going on. But if you want to try this later, totally cool to do that. I was going to do it in class, but. So chop it and boil it to separate the flavin. This is like the pH indicator. So you're going to have like this purple liquid. So when it is purple, it's neutral. So let me draw a good beaker and make several copies of it so I don't have to keep drawing it. Alright. Alright, so let me make some copies of this so I don't have to do it over and over. So I'll drag this one down here. This one right here. And this one right here. And this one will go like that. Alright. So let's color these in. Nice and purplish. Yeah, that's good enough. So I'll color this in nice. Nice as we can. Make it as accurate as possible for you guys. Alright. So when it's purple, it's neutral. So what you're going to want to do is, let me finish coloring these in, because otherwise it's going to take me forever when I'm explaining stuff. I don't like that. So color all these in. You're going to need red, purple, and green. And then let's get some nice green in there. Okay, so what you're going to do is you divide the liquid into several different, I mean, you can just use cups. It's not like you're doing mad science experiments. So divide the liquid in 3 cups. With different substances. Preferably something that's not crazy. So you could use like vinegar. Don't use any like crazy household cleaners or anything, but I mean, you could use like baking soda. And then you could see that. Trying to think if there's anything else really. Yeah, just use like baking soda and vinegar is pretty easy. Or you can even mix in like some coffee or like a little bit of coffee grounds or something like that. It'll change the color. So divide the liquid into separate containers with different substances and observe the color change. So right here is neutral, meaning it's around 7. So neutral. If it's red, it's acidic. If it's green, it's basic. So if you guys want to do that, it's pretty cool, but I mean, I'm not going to force you guys because I know it's kind of hard to go to the store and get red cabbage. Alright, so we're going to go on to calculating pH. We're going to go over it really quickly, and then next week we're going to really delve into it. I just wanted to expose you guys to it. So, calculating pH. This is the fun part. And we're not really going to do too many crazy calculations. I don't think we might. I haven't decided yet. Calculating. I have to remember when I did ice tables. I think I did that later on in my chem classes, but I don't know. So, pH has something else called pOH. So, the scale is out of 14. 14 equals pH plus pOH. To calculate pH, if you have the concentration of hydronium, like I showed you in autoionization where you get that is how you would calculate it. So you get negative log of H3O. And just to be clear, there's no such thing as a negative logarithm. Just so your math teachers don't get mad at me. Negative log implies that you have -1 times the log of n or x or whatever. Alright, so we're going to do some examples. And then we're going to go on to bases, and then we're going to call it. So, because I'm gonna give you some more examples where we have a little bit harder. We're gonna probably have like some chemical reactions in there and stuff. All right, so let's do example 1. We have, what is the pH of a 0.00010 molar solution of nitric acid? This is going to give you an idea of how strong this stuff is, because you'll see what I'm talking about. So our hydronium equals 0.00010. So all we have to do is pull up our calculator, clear out the stuff from last lesson, negative log of 0.00010, and get our answer. So our pH is going to be 4. Now, if you have the TIXA or 30XA or whatever it is, the small little one, you're going to do it a little differently. You're going to do log of 0.00010, hit enter, and then you'll hit negative. And then on your calculator, it's going to switch it over to the right answer. Not on this one, you'd have to do negative answer, and then it would give it to you. But on your calculator, you just hit the negative button. If you have any questions, come to office hours and show me your calculator on the camera. I'll explain how to do it. I have one at home, so I can easily explain it. All right, so your answer would be a pH of 4, which is still pretty strong. Anyways, because it's a logarithmic scale, so everything is like 10 times stronger or 10 times weaker. All right, next thing. Calculate the pH of a 0.2 molar solution of a strong acid. And just so you know, this really only works for the strong acids. With the weaker acids, you have to do a ice table, which I don't even know if we're going to do because that might be higher level. I have to double check. All right. So, but if you take AP Chem with me next year, you're for sure doing ice tables. So if I go over them now, it'll just help you. Now, calculating the pH of a 0.2 molar solution of strong acid. So we do negative log of 0.2 and then figure out what our pH is. So negative log of 0.2 is equal to a pH of about 0.7, which is super strong. And then that's how you really calculate based on if you have the hydronium concentration. Bases are a little different. So with a base, we have to calculate the pOH. So negative log of the base concentration, or OH, whatever you want to write, equals the pOH. So if you remember, 14 equals pH plus pOH. So here's how we're going to do this. So to get the pH, you would have to subtract this out. So it would be 14 minus pOH equals pH. Which, if you can imagine, it's going to be super high. So what is the pH of 0.0136 molar solution of potassium hydroxide? So let's do this. First, we find out the pOH. So pOH. pOH is negative log of 0.0136. So let's do that in the calculator. Negative log 0.0136. And then that's going to be about 1.87. So now we do 14 minus 1.87 equals pH. So that's going to be 12.13. All right, and then I'm going to do, that should be good enough. We're going to go over this more in depth next week, but I really wanted you to be able to calculate it so you understood for your lab what I was asking you to do. The lab is not due this Sunday. It's due the Sunday afterwards. But what I am going to be collecting this week is you have to turn in the actual data sheet. Your report is going to be due the week after. So I'm going to put that all in the announcement. Just make sure you do the lab and do all the calculations and stuff like that. And that is it.